A deck double-ended queue is a linear data structure that lets you add and remove elements from both ends. Think of a hallway with a door at each side. People can walk in or out through either door without disturbing the line inside. Push front of X, insert element X at the front left side. Push back of X, insert element X at the back right side. Pop front, remove and return the element at the front. Pop back, remove and return the element at the back. Front, look at the front element without removing it. Back, look at the back element without removing it. Size and number of stored elements. Empty, true if size is 0. Invariance that must always hold. The order of elements is preserved except when an operation explicitly changes it at an end. If we list the elements from front to back as a 1, a 2, a k, after any sequence of deck operations, the list will still be a prefix of the earlier list, with possible new elements added only at the two ends. Size is never negative. It equals the number of successful pushes minus the number of successful pops. The elements returned by front and back are always the first and last elements of the internal sequence, respectively. These invariants make reasoning about algorithms that use a deck much easier, because you never have to worry about hidden rearrangements inside the structure. The most common way to implement a deck in an array is to treat the array as a circular buffer. Imagine a circular racetrack. When a runner reaches the finish line, they continue at the start line without stopping. The array holds the data and two indices, head, pointing to the front element, and tail, pointing just past the last element, move around the circle using modular arithmetic. Capacity equals C, which is the length of the underlying array. Head equals 0, the index of the front element. Tail equals 0, the index 1 past the back element. Insert at front, head equals head minus 1 plus C modulo C. Data at index head equals X. Insert at back, data at index tail equals X. Tail equals tail plus 1 modulo C. Remove from front, X equals data at index head. Head equals head plus 1 modulo C. Remove from back, tail equals tail minus 1 plus C modulo C. X equals data at index tail. When head equals tail after a push, we know the buffer is full. The usual strategy is to resize the array to twice its size, copy the existing elements in order, and reset head to 0 and tail to the old size. Amortized big O of 1 proof. We use the accounting method. Charge each normal push or pop 3 units of credit. 1 unit pays for the actual constant time work, and the remaining 2 units are saved on the element being inserted. When a resize occurs, cost equals copy old size elements. Each of those elements already holds 2 saved credits, enough to pay for moving itself. The total extra credit collected before the resize is at least the cost of the resize. Therefore, the average cost per operation stays bounded by a constant. Hence, every deck operation runs in amortized big O of 1 time, even though a single resize may take big O of n time. The index arithmetic modulo C guarantees that all pointer moves are constant time, and the circular layout ensures that we never need to shift a whole block of elements, as we would in a naive array queue. A deck can also be built from a doubly linked list. Each node stores 3 fields. Struct node, value the stored element. Prev node, pointer to the previous node, null for the front. Next node, pointer to the next node, null for the back. 2 external pointers, head and tail, always reference the first and last nodes. Insert at front. Create a new node n with value equals x. Set n next equals head. If head is not null, set head prev equals n. Update head equals ns. If the deck was empty, also set tail equals n. Insert at back mirrors the steps, swapping prev and next and head and tail. Removal simply rewires the neighboring pointers and frees the node. Again, O1. Space-time analysis. Time, every operation touches only a constant number of pointers, so push front, push back, pop back, front and back are all theta 1. Space, each element incurs 3 fields, value plus 2 pointers. The overhead per element is therefore O1, giving total space theta n for n stored items. The list also needs 2 extra references, head and tail. Compared with the circular buffer array, the linked list version never needs to resize, but it uses extra memory for the pointers and suffers from poorer cache locality because nodes are scattered in memory. Both implementations satisfy the same logical invariance described earlier. They just trade off different practical costs. One of the most celebrated algorithmic uses of a Deque is the sliding window maximum or minimum problem. Given an array as 0 to n-1 and a window size k, we want the maximum value in every contiguous subarray of length k. The Deque stores indices of array elements, kept in decreasing order of their values. This way, the front of the Deque always holds the index of the current window's maximum. Step-by-step example. Array 2 1 5 3 4, k equals 3. I equals 0, value equals 2. D is empty, pushback 0. D equals open bracket 0, close bracket. I equals 1, value equals 1. 1 less than or equal to a D back equals 2, pushback 1. D equals open bracket 0, comma 1, close bracket. I equals 2, value equals 5. 5 greater than a 1 equals 1, pop back, remove 1. 5 greater than a 0 equals 2, pop back, remove 0, push back 2. D equals open bracket 2, close bracket. I greater than or equal to k minus 1, output a D front equals a 2 equals 5, first window maximum. I equals 3, value equals 3. 3 less than or equal to a 2 equals 5, push back 3. D equals open bracket 2, comma 3, close bracket. Remove indices out of window. I minus k equals 0, D front equals 2 greater than 0, keep. Output a 2 equals 5, window 1 5 3. I equals 4, value equals 4. 4 greater than a 3 equals 3, pop back, remove 3, push back 4. D equals open bracket 2, comma 4, close bracket. Discard out of window index. I minus k equals 1, D front equals 2 greater than 1, keep. Output a 2 equals 5, window 5 3 4. Resulting maxima are 5 5 5. The algorithm runs in big O of n because each array index is pushed and popped at most once. The same idea works for sliding window minimum by keeping the Deque in increasing order. This technique appears in many real-world systems, monitoring the highest CPU load over the past minute, calculating rolling stock price peaks, and so on. A priority queue is an abstract data type where each element carries a priority, often a numeric key. The queue always gives access to the element with the extreme priority, the smallest for a min priority queue or the largest for a max priority queue. In a binary heap representation, the structure is a complete binary tree stored in an array. The heap order property guarantees. For a min heap, for every node I, key of parent I is less than or equal to key I. For a max heap, for every node I, key of parent I is greater than or equal to key I. This local condition ensures that the global extreme element resides at the root array index 0 or 1. Primary operations. Insert X adds a new element with its key. Find min or find max returns the root element without removing it, O1. Extract min or extract max removes the root and array heapifies, O log n. Decrease key lowers the key of the element at position I in a min heap and restores order by moving it up. O log n. Some implementations also support increase key for max heaps. All these operations rely on the heap order property, which makes the structure much faster than a naive unsorted list, where extract min would be O(n). A binary heap stores the tree in a plain array because the tree is complete. Every level except possibly the last is fully filled, and nodes are left justified. This allows index arithmetic to locate parents and children without explicit pointers. Parent of I equals open parenthesis I minus 1 close parenthesis divided by 2. Left of I equals 2 times I plus 1. Right of I equals 2 times I plus 2. The root is at index 0. Function sift up open parenthesis I close parenthesis colon, while I greater than 0 and heap parent of I greater than heap I colon swap heap I with heap parent of I. Then set I to parent of I. Each swap moves the element one level up, and the height of the heap is floor of log base 2 of n. Therefore, at most floor of log base 2 of n swaps occur, giving big O of log n time. Function sift down open parenthesis I close parenthesis colon. While left of I is less than size colon set smallest to left of I, if right of I is less than size, and heap right of I less than heap left of I, then set smallest to right of I, if heap I less than or equal to heap smallest break otherwise swap heap I with heap smallest, then set I to smallest. Again, the element can travel at most the height of the tree, so the cost is big O of log n. To turn an arbitrary array of n elements into a heap, we call sift down on every non-leaf node starting from the last parent floor of open parenthesis and minus 2 close parenthesis divided by 2 down to 0. This is called heapify and runs in linear time. Overall, the binary heap gives us insert sift up gives big O of log n amortized O1 if we allow a lazy build. Extract min swap root with last element shrink size. Sift down gives big O of log n find min just red heap 0 gives O1. These bounds hold for both min and max heap variance with the comparison direction flipped. A complete binary tree with n nodes has every level completely filled except possibly the last, which is filled from left to right. 2 to the h less than or equal to n less than 2 to the h plus 1. H less than or equal to log base 2 of n less than h plus 1 implies h equals floor of log base 2 of n. Thus the height of a binary heap containing n elements is exactly floor of log base 2 of n. The naive way to build a heap would insert each element individually, costing big O of n log, and the bottom-up method works in big O of n by exploiting the fact that most nodes are near the leaves and therefore require little work. Consider the work needed to sift down a node at depth d, root depth equals 0. The maximum number of swaps it can perform equals the height of its subtree, which is h minus d. The number of nodes at depth d in a complete tree is at most ceiling of n divided by 2 to the d plus 1. W less than or equal to sum from d equals 0 to h minus 1 of n divided by 2 to the d plus 1 times h minus d equals n times the sum from d equals 0 to h minus 1 of h minus d divided by 2 to the d plus 1. The series sum from k equals 1 to infinity of k divided by 2 to the k converges to a constant, specifically 2. W less than or equal to 2n implies w equals big O of n. Because the constant factor does not grow with n, the whole heapify process runs in linear time. This result is essential. Building a priority queue from a bulk list of keys can be done in big O of n rather than big O of n log n. The proof is often required in exams to show understanding of amortized analysis and summations. Operation column, binary heap column, binomial heap column, Fibonacci heap column. Insert binary heap big O of log n, binomial heap big O of log n, Fibonacci heap big O of 1 amortized. Find min, binary heap big O of 1, binomial heap big O of log n, Fibonacci heap big O of 1. Extract min, binary heap big O of log n, binomial heap big O of log n, Fibonacci heap big O of log n amortized. Decrease key, binary heap big O of log n, binomial heap big O of log n, Fibonacci heap big O of 1 amortized. Merge union, binary heap not supported needs big O of n, binomial heap big O of log n, Fibonacci heap big O of 1 amortized. A binomial heap is a collection of binomial trees b sub k where a tree of order k has 2 to the k nodes and exactly k children, each being a b sub k minus 1, b sub k minus 2, and so on down to b sub 0. The heap maintains the min heap order inside each tree. The set of trees corresponds to the binary representation of the total number of elements, at most one tree of each order. Insert creates a single node tree b sub 0 and merges it, big O of log n, because we may need to carry through several orders like binary addition. Merge is analogous to adding two binary numbers. We walk through the orders once, big O of log n. Extract min removes the root of the tree containing the minimum, then breaks that tree into its constituent subtrees and merges them back, big O of log n. Proofs often ask you to argue that the number of trees is at most floor log base 2 n plus 1, so each operation touches only a constant number of trees per order. A Fibonacci heap relaxes the strict shape constraints of binomial heaps. It stores a forest of trees that are almost binomial. The degree of a node is bounded by big O of log n, but the trees can be irregular. Insert simply creates a new singleton node and adds it to the root list, big O of 1. Merge concatenates the two root lists, big O of 1. Decrease key cuts the node from its parent and moves it to the root list. If the parent has already lost a child, a cascading cut continues upward. Using a potential function phi equals number of trees plus 2 times number of marked nodes, we show the amortized cost is big O of 1. Extract min removes the root with minimum key, merges its children into the root list. then performs a consolidation step that repeatedly links trees of equal degree, similar to binomial heap merge. The amortized bound becomes big O of log n because the degree of any node is at most floor log base phi n, phi approximately 1.618, derived from the Fibonacci recurrence. Typical exam questions ask you to 1. Define the potential function and prove that each operation's amortized cost matches the table above. 2. Show that a node of degree d must have at least f sub d plus 2 descendants, implying d equals big O of log, and these proofs combine combinatorial arguments, Fibonacci numbers with amortized analysis, demonstrating deeper mastery of priority queue theory. In practice, Fibonacci heaps are valuable when a problem performs many decrease key operations. For example, Dijkstra's shortest path algorithm, while binary heaps are simpler and have better constant factors for typical workloads.